recording here. All right, we're going to continue on with this chapter. All right. Then let's go with why this acid catalyzed helps us in other methods too. We get the same structure when we do oxymercurization, demercurization. We get the same kind of intermediate when we have bromination. When we have bromine adding across a double bond, remember we get anti-addition for that, and we get very specific for that. These same kinds of intermediates happen in the epoxy, where we have this elongated bond where the more substituted side is going to be attacked by the nucleophile. We have an elongated bond where the more substituted side is going to be attacked by the nucleophile. And when we did reactions of alkenes to make alcohols with mercury, we saw that same concept where we had the reaction of the nucleophile with the more substituted carbon. And it's all basically the same kind of intermediate with this elongated bond between the positively charged species on the top and that partially positive, more substituted carbon. Okay, so you can actually draw this conclusion in our oxymercurization, our bromination, and now for our substituted epoxies as well. Okay, so let's talk about the regioselectivity, and then we're going to also talk about the stereoselectivity of these things. Okay, so in the concept of the acid catalyzed system, we are still creating our three-membered ring. So our three-membered ring is blocking the top half of our compound. The only thing acid is doing for us is it's making the more substituted side the more positive side, and therefore that's the one that's going to react with the nucleophile. Okay. However, that nucleophile must come in from the bottom side of the molecule. If it has to come in from the bottom side of the molecule, we have regioselectivity because of the substitution, the electronic properties, but we have stereoselectivity because of our three-membered ring blocking the top. Okay. So in the case of this system, we can start with this methyl ethyl epoxy compound right here. And if we do our stereochemistry around here, we'll find out that's the R configuration. And like all SN2 reactions, we get inversion of stereocenter from the system. Okay. Notice we're not breaking this. We're not forming a true carbocation. We're forming an elongated, partially positive carbon and an elongated bond. That means we will do an SN2, which means we end up with inversion of the stereocenter. Okay, so that means that we can choose whether to have the steric or electronic effects be dominant. Okay, if we want steric effects to be dominant, do it in the absence of acid or under basic conditions and use pretty good nucleophiles. If you want to be very regiospecific, you can choose whether to use acid if you want the more substituted nucleophile attack part and the less substituted alcohol, or if you want the more substituted alcohol, you can choose to do it in neutral or basic conditions. Okay. Now, we've also know, because we have the top half of the molecule in both the protonated and unprotonated form is blocked by the epoxy, we know that we're going to get stereospecificity because it has to come in from the bottom. And we know it's an SN2 reaction, so we know we're going to get inversion. Okay. So let's look at that one more time in kind of detail. Okay. So we're going to use these rings to make it easy to show you that it's not flipping around, and we're looking at that. So we're looking for the stereospecific part of this reaction here first. Okay. So in this case here, we're going to start with our neutral species right here. And we have assigned this one as R and this one as S. And well, sorry, this one is S and this one is R right here. And of course, the first thing that's going to happen under the protic system is we're going to protonate that ring and elongate that bond. Which way is it going to elongate? It's going to elongate to give the partial positive charge on the most substituted carbon. Fortunately, the methyl group makes this carbon a tertiary carbon. So that means our new nucleophile, which is our bromide ion now, so imagine we just added HBr to the system, has to attack anti to the oxygen here. It must attack anti because the oxygen is blocking the top. So when we do that, we have stereospecific reaction. Our alcohol is still on the top here, and therefore we still have the S configuration. However, the methyl group has now flipped from 1 because of inversion to up here, and our priority has changed as well, but that also makes it into the opposite priority system, and it is now S again. Do we see that this always gives us that inversion product if we use that acidic system because we're blocking the top? That's the key. Now, well, what if it's blocking the bottom? Well, do we see the same thing? Well, yes, you're blocking one side of the molecule. So if we just flip the molecule over and use the other configuration of it, so notice this side is now R and this side is now S. So this is the enantiomer of the top one. What we're going to see is we're going to see protonation. And again, the carbocation is going to form on the more substituted carbon. Okay. If the the partial positive charge, not a full carbocation, the elongated bond is going to give it on that more substituted carbon, but the oxygen's now on the bottom. So the nucleophile has to come in from the top, and again, affecting the regiochemistry, and we're going to end up with the RR because we had inversion of that stereocenter because of the anti-addition. Okay. So do we see it's both regioselective and it's stereoselective? All right. Okay, so I told you we're going to talk about a little more of oxidation of aldehydes and ketones. So we can use other reagents to do this same kind of oxidation. But in the case of these other reagents, they're kind of, the first two are derivatives of the chromic acid. The Jones reagent was the one we talked about before. We can actually use a salt of it, and we can use it in water as well. And what it will do is both of these reagents will continue to oxidize it down to that carboxylic acid. A new reagent we haven't talked that much about what we did in the alkenes chapter is the potassium permanganate. Now this works better for things that already have some group on there, and it's done under basic conditions. And the great thing about that is some things aren't really soluble in acidic water, but you can pull them into basic water, and it makes these really a good target. So if you have something that does dissolve in acidic water, you can do the Jones reagent system. But if you have something that dissolves in basic water, like alcohols or other carboxylic acids already in the group, then you can use the permanganate system. But they both do the same thing, where they will take primary alcohols down to carboxylic acids because of the presence of water. Okay, and the presence of that other hydrogen that can be transferred. All of these reagents will all take all secondary alcohols down to ketones and then stop. And again, all tertiaries don't react at all because there's no hydrogen to pull off here. Without that hydrogen to pull off, nothing happens. Because then we have an R minus or an R plus as a leaving group, which is a horrible leaving group. All right, questions on that, or the stereospecificity of the ring opening reaction with epoxies. All right, so the last topic we're going to talk about today is what we call conversions of alcohols to better leaving groups. Okay, so we did a little of this in our alkyl halides chapter, but we're going to go a little bit deeper in that. But we're also going to show you other ways to make alcohol a really good leaving group. Alcohol by itself is a bad leaving group because it's leaving as hydroxide, which is a fairly strong base. So our first trick for that is to protonate it and turn it into something that can leave as neutral water. Okay, so imagine we have either HBr or an acid plus sodium bromide such that we have bromide around as a nucleophile. First step in any acid catalyzed system is the protonation of your Lewis base, which in this case is the alcohol. And now we can have attack by one or the other of these nucleophiles. This is not a very strong nucleophile, so the bromide is the major nucleophile in the system. leading to our alkyl bromide, regeneration of water, and then we end up with our conjugate base of the sulfuric acid. Okay, this works really well with HBr. HBr has just the right amount of nucleophilicity to make this thing happen. However, this doesn't work very well with HCl. The chlorine is not as nucleophilic as the bromine, remember, because it's smaller. You know, iodine's more nucleophilic than bromine, and chlorine and fluorine are not as good a nucleophile. So this reaction doesn't happen without a catalyst, okay? Now, in this catalyst here, we're not using the acid as the catalyst. We're using a different Lewis acid. And we're going to see this a lot next semester. We're going to add a catalyst to the system. A lot of times they are what we call Lewis acid catalysts. Imagine things that are, you know, partially positive or will react immediately with a Lewis base. This particular one is called zinc chloride. And zinc, this is zinc +2 in chloride here. So the first thing that happens is we have our Lewis acid base reaction. Our Lewis base is our primary alcohol. Our Lewis acid is our zinc chloride, and it forms a complex. Now this complex now would leave as a neutral species. And notice that it probably has a little bit more polar bond between that oxygen and that zinc, making it an even better leaving group than water by itself. Okay, because it's more polar bond, it's taking more of the electron density toward the zinc, making these electrons easier to come back to the system. Now we can use a weaker nucleophile in the chloride ion to displace that better leaving group than water. And then we generate our alkyl halide plus this compound. Now this compound's not really stable and actually will decompose in the presence of acid to regenerate our Lewis acid and one equivalent of water. Okay, so it only takes a trace amount of this zinc chloride to get it to go. Okay, but do you see how we're using something to make that oxygen a better leaving group? Hydroxide's a bad leaving group. Neutral water is okay if you have a strong enough nucleophile. But as your nucleophile strength goes down, we have to make it other ways to make that a better leaving group. Okay. In addition to this zinc chloride HCl, we have another way of adding halides to our system. And it works really well with bromine and iodine. Not so well with chlorine, which is why the zinc chloride system is actually there. Because again, the chlorine's not as good a nucleophile, and so it's not as useful a reaction. Okay, and in all these cases, we're using some kind of phosphorus and halogen system, and it'll transfer all three of those halogens off of there to give us one equivalent of phosphoric acid and three equivalents of our alkyl halide. So we have to start with three equivalents of our alcohol. Okay, so in this process, what we're doing is we're making sure that phosphorus is actually changing oxidation state over time, and phosphorus is something we call is oxophilic. It loves being bonded to oxygen. It's naturally found as phosphates in nature. It's rarely found as phosphorus metal in nature, and so it wants to be in that state. So any chance it has to abstract these oxygens, it will. Now, the phosphorus triiodide is actually not very stable. So a lot of times you actually make it in situ, where you just add two equivalents of phosphorus to three equivalents of iodine. And then that will also create this in situ or in the reaction. And it'll generate your alkyl iodides as well. But they all work basically by the same mechanism. Okay. So that mechanism is going to start with the idea that we, number one, have our phosphorus in a non-aqueous place. Okay. We can't have water there because it'll react with the water faster than it'll react with your alcohol. So we start out in a non-aqueous solvent, and we have our reactive species here, our phosphorus tribromide and our alcohol. So in this case, our alcohol is now acting as our Lewis base, and we'll get this reaction to progress to give us our alkyl halide, and eventually it'll give us our phosphoric acid. Now, it's kind of drawn weird like this. If we looked at the tautomer format, it'll actually rearranges so the hydrogen goes here and you get a double bond. So it actually kind of goes back and forth. So this is actually the major isomer, but this is one of the contributing tautomers to it. So either one is appropriate to use. Okay. But this is definitely the product in most of these systems. Okay. So how does it work? Well, cool thing is it's an SN2 reaction. So that tells us some things about, number one, stereochemistry, tells you that we're not going to rearrange anything, but it tells us we had a good leaving group and a good nucleophile. So let's find that good leaving group, good nucleophile to make this SN2 reaction happen. So the first thing we have happen is phosphorus here is actually electron poor, believe it or not. Even though it has that lone pair on there, it's down one on the periodic table, and it can actually have up to 10 electrons around it and still be satisfied. So we're going to use our alcohol as our Lewis base. We're going to use our phosphorus as our Lewis acid, generating our first intermediate here, which is now a really good leaving group. We have a phosphoester here. This is an inorganic phosphoester. And we generated an equivalent of bromide ion. That bromide ion is a good nucleophile and will come in and attack the backside of here. When it does so, it leaves the alkyl halide plus this compound here. Okay. This compound, the phosphorus is still a Lewis base. It is still electron deficient, and it has two equivalents of bromine to transfer. So it's going to do that same reaction again, liberating a bromide ion as the nucleophile, and that's going to attack. And then it'll do it one more time until you've consumed it all, and we have our phosphorus, phosphoric acid, and all of our equivalents. So this is two more equivalents from the first one we made. So that's a total of 3 equivalents of alkyl halide for every 1 equivalent of the phosphorus trihalide. Okay. Okay. So do we see why we're generating a better leaving group? Do we see why the bromide is being liberated and it turns it into the nucleophile and allows the reaction to progress? Okay. All right. So that makes it really cool. That means the reaction is stereospecific because it's SN2. So that means we'll always get inversion of stereocenter. The fact that we made that inorganic phosphate ester is that it doesn't leave first. We do not generate carbocations. If we do not generate carbocations, we do not have a rearrangement. And because it's an SN2 reaction, we don't have any E1 or E2 products out of it either. And we get a very selective replacement of an OH with a bromine with stereo chemistry inversion. So that is really good about this. It's very consistent, very reliable, and gives us the same products every time. Okay. Now, I said that that reaction with the chlorides doesn't work as well with the alkyl, with the bromides and the iodized phosphate bromides. And that has to do with the fact that chloride's not as good at a leaving group. So we have a different reaction for this. I'm sorry, chloride is not as good a nucleophile. Okay, so we have a way around this to make it the oxygen an even better leaving group. And we use a thing called thionyl chloride, SOCl2. We introduced this in the alkyl halides chapter, I think, but we're going to do it again. But we also want to show we can use the same reagent under 2 different conditions, and we can change the stereochemistry of a secondary alcohol. Okay, primary alcohols, we really don't have stereochemistry because we don't have that other substitution, but in secondary alcohols, we do see it. So the key here is if we use thionyl chloride in the presence of a base, in particular pyridine, which we just introduced above in PCC, if we do it in the presence of pyridine, we get inversion of configuration, meaning it goes an SN2 mechanism. Okay. If we do it in the absence of pyridine, in something like diethyl ether, we actually end up going through a special SN1 reaction. And therefore we get retention of configuration. I'm going to do SN1 star. And it's an SN1 star, and I'll show you why in just a minute. Okay. So let's do the first one, the SN2. So in the SN2 reaction, there's a lot of steps in here, but the idea here is we have our Lewis base, we have our sulfur as our Lewis acid right here. Even though there's that many electrons around there, sulfur can have up to 10 electrons around it. So it acts as the base, generating our new sulfur oxygen bond. When it does that, we get a little rearrangement and it kicks out a chloride ion. When it kicks out a chloride ion, that chloride ion is now a nucleophile, but we still don't have a good enough leaving group yet. So what happens is the pyridine acts as a base to deprotonate it to give us this alkyl chlorosulfate right here. Okay, well, even that alkyl chlorosulfate is not a really good leaving group yet. Okay, so now we have our pyridine acting as our base, Lewis base, attacking our sulfur is our Lewis acid, giving us another intermediate here that kicks out another equivalent of chloride. At this point here, we now have 2 oxygens and a nitrogen on sulfur, and now it's a great leaving group. Now even the poorly nucleophilic chlorine could come in and displace it here. And because it's displacing it in an SN2 type reaction, we get inversion of stereocenter. And then once that kicks out here, we actually decompose it to SO2 and we regenerate pyridine. Okay. So the cool thing about that is that SO2 is liberated. We get rid of that. It goes off as a gas. We regenerate our pyridine catalyst. So you can do this reaction with just a drop of pyridine catalyst, and you'll always get inversion of stereocenter because it'll always be an SN2 reaction. Okay, so this is a nice clean SN2 reaction. Okay. Now, let's do it the other way in the absence of pyridine. In the absence of pyridine, things change a little bit. Our first thing that happens, we still form that sulfur chlorine compound. I mean, that sulfur oxygen compound right here, and we generate a chloride, but now our chloride is the only base found. Okay, our chloride ion is the only base available to us. So the chloride ion acts as a base and deprotonates our complex and gives us our same intermediate, our alkyl chlorosulfate. Okay. So the problem is that alkyl chlorosulfate is, it's not a great leaving group, but it can leave. But when it does leave, it leaves by homolysis. By heterolysis. What it does is it leaves giving you a carbocation right here. And this carbocation is in what we call an intimate ion pair, meaning that as soon as this breaks, this has a positive charge and this has a negative charge. So now they're attracted back to each other. Okay. So like we're breaking apart because we have a weak bond, but we don't have time to move away from each other. Our solvent doesn't support ions very well. Okay. Notice we're doing it in ether. So they're kind of stuck there together. And if they're stuck there together, now the chlorine is, can act as a base. If one of these oxygens acted as a base, we just go back to the original material. But if the chlorine acts as a base, it's going to be on that same side it just broke off of. And if it's on that same side it just broke off of, it's going to regenerate that new chlorine carbon bond. But now we have a positively charged chlorine, and the easiest way to lose that is to pull this and break off SO2, and we have chlorine. But notice that chlorine is on the exact same configuration as the alcohol was. It has everything to do with, we just broke apart to form 2 ions, but we can't dissolve away from each other. Our solvent doesn't allow that. And so what happens is we're going to transfer along that same interface where we just broke apart that chlorine 2, and that generates our retention in stereo configuration. So that's why I called it a special SN1 mechanism. It doesn't, allow you to just have a solvent. Remember, polar protic solvents support carbocations, and they can float around until we have a poor nucleophile right here. In this case, we have them so close together and not dissolving away from each other that we had to find a nucleophile somewhere in that contact pair. And the nucleophile in that contact pair is that chloride, the chlorine. And that's why the chlorine reacts, and that's why it's a SN1 mechanism. All right, questions on that? Okay, let's see. So the last thing I want to talk about is a group called the sulfonates, okay? This will only take a couple minutes, so I'm gonna go a little long, I apologize. So the idea here is that we're gonna create a sulfur oxygen bond and generate a chloride ion. Usually we use a base to do it. And what this does is this creates a whole set of sulfonic acid groups. And sulfonic acids are very, very strong acids, which makes them very weak bases. And very weak bases are really good leaving groups. So we have a whole bunch of different derivatives we can do. We have methyl group here, which is called the mesylate or methylene sulfonic acid. We have the toluene group, toluene sulfonic acid or tosylate, or even the trifluoromethyl group here, which is called the triflate. It doesn't matter which one you use. The key here is that now you've created, once this group leaves with the oxygen, that's a very strong acid and therefore a very weak base, and a very weak base makes a great leaving group. So we can convert any alcohol into a great leaving group by using one of these chlorine sulfonic acids and generating that intermediate. And now we can start attacking with even weak nucleophiles to displace that really good leaving group. And the key here is you have retention of configuration when you form the leaving group, and then you have inversion of center when you have it leave, okay? So it only attacks the oxygen, it doesn't break the oxygen-carbon bond, so that when you have your nucleophile come in and displace it, you get inversion of center, but creating the sulfonate retains that configuration. So you know exactly your stereochemistry of your system. Okay, and we dehydrated alcohols in chapter 9, so we're not going to do that. Questions on that? Okay, I'm going to go ahead and stop recording, and you can ask questions